Okay, so it's my pleasure to introduce Carlos Shabatzi, who will speak to us today about the heterotic Ricci flow and its three-dimensional solitons. So thanks, Carlos.
So thanks a lot for inviting me to contribute to this online seminar. So I'm going to be discussing some work in collaboration with Andrei Moroianu and Angel Murcia. Andrei Moroianu is in Paris, and Angel Murcia is currently a postdoc in Padua, I think, Italy. So the main goal of this talk is to discuss the basic aspects of a novel curvature flow that we have chosen to call the heterotic Ricci flow, and more specifically discuss its three-dimensional soliton, so its three-dimensional self-similar solutions. So I won't say that much about the flow itself.
Carlos, are you there?
Can you hear me?
Now, yes, but your camera freeze for a moment. So maybe you should turn off your camera.
Yeah. Sorry about that. I'm gonna do that. How do I do this? 1 second. Sorry. There you go. And there you go. Can you hear me now?
Yeah, good. Yeah, everything is good.
Sorry about that. If this gets worse, I can connect through my phone, but I don't know. Anyway, so as I was saying, I'm going to discuss this curvature flow that we have chosen to call the heterotic Ricci flow, and which is motivated by being the two-loop renormalization group flow of the heterotic string common sector, which I will explain in more detail in a moment what it means from a mathematical perspective, of course, because there is some deep physics hidden behind those words, which I'm not going to get into because that's way beyond my pay grade. And then I'm going to focus on discussing a certain class of solitons of this flow. So this flow, I won't discuss any analytic properties of this flow, which remains to be explored, but I will focus instead on the solitons of this flow because they relate deeply with solutions of heterotic supergravity. So some of the main characteristics of this curvature flow, this heterotic Ricci flow, is that it depends on a parameter, which is positive, can be chosen at will, and involves the evolution of a family of metrics and a family of three forms, which are subject to certain equations. And it involves two terms, which are quadratic in the curvature of a metric connection with skew torsion. And as I was saying, solutions of a particular class of solutions of this heterotic Ricci flow gives solutions to heterotic supergravity with trivial gauge band. And I will also discuss the relation between the heterotic Ricci flow, heterotic supergravity, with solutions of the Hall-Strominger system, of the celebrated Hall-Strominger system. Okay, so, well, this heterotic Ricci flow is related to several evolution flows already existing in the literature. The most important one, which would be the classical Ricci flow, is obtained by taking this parameter kappa, on which the system depends, and this family of three forms to be zero, and then you recover the classical Ricci flow. When you take only kappa equals zero, but you keep the family of three forms evolving, then you obtain the RG2 flow. So, sorry, I was confused for a moment. When you take kappa equals zero and you keep the family of three forms evolving, then you obtain the generalized Ricci flow, which I will discuss also briefly in a moment. And when you take h equals zero, now this is the case that I was meaning before, and kappa positive, then the heterotic Ricci flow reduced to a constrained form of the RG2 flow, which has been discussed in the physics as well as in the math literature. And it has a similar origin as the heterotic Ricci flow, but it doesn't involve a string theory, as I will explain in a moment, but a nonlinear sigma model coupled to a Riemannian metric. Also, this heterotic Ricci flow, when restricted to a complex manifold, is expected to be related both with the anomaly flow and the pluriclose flow, although the relation may be subtle and it hasn't been established yet. More generally, from the perspective of generalized geometry, I believe this heterotic Ricci flow is natural within generalized geometry, and it should be, in particular, a particular case of the generalized Ricci flow that Mario introduced on a transitive Courant algebra. So I will discuss also this very briefly in a moment. But, well, this hasn't been proven yet, but I think it should be a particular case of this generalized Ricci flow. But instead of using an exact Courant algebra to define it, so on a more general type of Courant algebra. And also being this a renormalization group flow in string theory, it should be expected that it is related through string theory dualities with other curvature evolution flows inspired in supergravity, such as the type 2a, type 2b, and 11D flows. Well, there are many flows now in the literature, so I believe this heterotic Ricci flow connects to many of them, and in a particular sense, it can be thought of being as a parent to some of them. In a sense that I think will be clear after this talk. So in order to justify studying this heterotic Ricci flow, we have to begin at the beginning. And those of you who are familiar already with the generalized Ricci flow will know this part by heart, essentially, but I need to briefly review it. So our starting point is a theory, is a functional, which is defined on a given Riemannian manifold equipped with a true form and a function and a two-dimensional oriented manifold. So this is the data that you have to fix in order to define this functional. And then the variables of this functional are maps from this two-dimensional manifold into the target space M, which is this manifold, Riemannian manifold that we have fixed, together with metrics on this two-dimensional manifold. So there is some fixed data, G, a Riemannian metric on M, a two-form on M, and a function on M. And then there are variables of this action functional, which are metrics on X, and maps. And the action function, it consists simply of and then the dual of the pullback of the true form and this combination of the scalar curvature of the metric on the two-dimensional manifold. So this is a perfectly defined action functional for metrics and maps. And the configuration space of the theory admits a large automorphism group. And as part of this automorphism group, we have conformal transformations of the metric on X. And these are very important. So why are these very important? Because despite the fact that classically, for every choice of G, B, and Phi, we can obtain a perfectly well-defined classical theory through the Euler-Lagrange equations of the previous functional. If we try to quantize the theory, not every triple G, B, Phi will work. This is because these Weil transformations, these conformal transformations, are no longer a symmetry in the quantum theory. And therefore, they define an anomaly of the theory, namely, loosely speaking, a classical symmetry which does not survive the quantization process, right? That's a working definition of anomaly for a mathematician. So in order to deal with this type of problems and get rid of anomalies, physicists use several deep tools, but one of them involves this regularization procedure by which all the couplings of the theory acquire dependence on a cutoff, ultraviolet cutoff. that depends on the theory, the way it's implemented. But in this case, the couplings are tensors itself on this target manifold. So actually, the dependence on this of these couplings on this cutoff, which is usually measured by this renormalization group flow, becomes a particular set of evolution equations on a manifold for tensors, loosely speaking. This is the way physicists arrive to this type of equations. And then they show, proof, or argue that Weyl invariance, meaning these invariants under conformal transformations in the quantized theory, whatever that means, is restored if these beta functionals are equal to 0. Modulo time-dependent diffeomorphisms, this is something that I add because I think it's the right way to proceed. But the standard law is that this is restored when these beta functionals vanish. Very well.
Carlos,
so then yes.
Can you say something more about, so the Weyl invariance, can you go back to the slide where you show the action? Just one moment. So
Yes.
The Weyl invariance, you means conformal rescalings of the metric on the surface. Is that correct? Yeah.
On the surface, exactly.
Okay.
Yeah.
Okay. And this is, so the action is, I guess, on the nose Weyl invariance. Is that the point?
It should be, yes.
Okay, okay, yeah, I believe that. Yeah, okay. Okay, and this is what is spoiled when you quantize somehow. Okay.
Yes, this is what, yeah, that's the I don't know how is this spoiled because I haven't quantized these theories, but that's what's explained in the standard physics books. And the point here is that, well, these beta functionals, well, they need to be 0, but there are some subtleties there. But that's the standard law statement. I can mention what I mean by this in a moment, but
Okay.
yes, this is
That's
what
fine. I wanted to
usually...
understand.
Yeah. Okay, very well, thanks. So, okay, so now we have this source of evolution flows on manifolds coming from physics, but someone has to compute these beta functions, right? Because they are complicated objects and computing them is even more complicated. So people have done this at the lowest order in kappa, because computing them is usually a perturbative process. So you do it order by order in some parameter, in this case kappa. And when you do it, something happens, and this is the result of the computation at the 0 order in first order in kappa, sorry. And now this is very familiar to most of you. This is an evolution flow for a family of metrics, and a family of 3 forms, and a family of functions.
Sorry,
and,
what is, how does kappa appear in, is it related to the energy scale or is not?
Yes, exactly, because apparently, sorry, let me go back again. This kappa, which appears here, even if this is a global constant that classically is irrelevant, when you do the path integral, now it's relevant because it's in the exponential of the path integral. So it becomes the natural parameter to compute perturbatively. I'm far from an expert on this, but this constant, even if classically is not important, quantum mechanically it is, because it appears in the exponent of the path integral, right? So that's how it appears. But again, unfortunately, I haven't done this calculation. I wouldn't know how to do it. So I'm just picking up the results from the literature.
Sorry, Carlos.
Yes.
This is related with the length of the string.
Come again, sorry?
This is related with the length of string in the nonlinear sigma model, this kappa.
Yes, it's like the tension of the string, right?
Yeah.
or one of the inverse. Yeah. It's a meaningful constant, but I won't say much about the physics of this business, unfortunately, because I don't know much about it. So, but it appears there, and at zero order you get this system of evolution equations, and well, from these evolution equation for B, we obtain a corresponding evolution equation for A. And to note that the evolution of this function separate this in mind, and after rescaling appropriately, and forgetting about all higher order terms in this computation, we obtain the generalized Ricci flow in one of its presentations, at least. And well, you can go check the book by Mario and Jeff on the topic. But this is one of the ways to justify physically the generalized Ricci flow, is the first order renormalization group flow of the bosonic string.
Can you go back
Very
one
well.
slide? Yes, I wanted to see the
Yes.
So the evolution of the dilaton here is a constant plus kappa over 2 minus. So delta is what?
Is the formal adjoint of the exterior derivative. L2.
But on phi. Oh, okay. Phi d is the phi d. Okay. Yeah, you introduce a notation. Okay, yeah. Now I understand. Okay.
We will come back to this equation in a moment. So, well, the generalized Ricci flow, I guess we can say, is by now an active area of study in the literature. As I was mentioning, there is even a recent book on the topic, and it has several potential mathematical applications. And one of them is the classification of compact complex surfaces. And I refer to you to a nice review by Jeffrey on the pre-closed flow and the geometrization of complex surfaces for more details about this. And in any case, given the interest and importance of this generalized Ricci flow, and keeping in mind that it's the first order contribution of this renormalization group flow, the natural question is, what about higher order corrections? What happens to this flow if instead of stopping at first order, we go beyond first order? So in order to do this, something funny happens. When we did this for the generalized Ricci flow, so at first order, we did it in the bosonic string, but it wouldn't mind where we do it because this is a common sector of all string theories. But in order to go beyond the first order, we need to choose a particular string theory, and not that the result depends on the string theory we choose. So for several reasons, we have chosen to consider the heterotic string theory to compute the next order, or to obtain the next order. But it's interesting to note that if we choose a different string theory, then we would have obtained a different result. A priori, one would say that they are all related via string dualities, but well, whatever that means, that's very vague at this point. So let me remark again that we don't compute these higher corrections ourselves, but we interpret the existing literature, which is not so fun, but this is already done. So let's see what's what. So our first then.
Carlos, can I ask something?
Yes.
Just
sure.
a curiosity, but yes, I've never seen this written down with the alpha prime around, so with your kappa. So is there a conceptual relationship between the change? I mean, T is logarithm of the energy scale, right?
Yes.
You said this before.
Yes,
is there a conceptual relationship between this and kappa? Because this, I mean, you can rescale T and then you will get the usual, I mean, you can absorb T kappa in T somehow. So
yes, and we will do this to present the heterotic Ricci flow as it is done for the generalized Ricci flow. But probably there are, and probably the combination of T and kappa that one obtains after rescaling the way you are saying is meaningful. But I don't know if it has an interpretation. But I'm sure T times kappa or T over kappa has a physics interpretation, but I don't know. Probably.
Okay.
But
okay. Thank you. Yeah,
sorry. So we checked the literature and we extracted the following proposal for this renormalization group flow at second order now in kappa. So we have, of course, the result at first order corrected with this term, which we have written as RGT, HT, circle GT, RGT, HT. I will explain what is this, but this is in a moment. But this is just a contraction of a curvature tensor of a connection with torsion HT with itself, leaving only two indices free. So this is the only correction we get for the evolution of GT. The evolution of HT is modified, and then the evolution of alpha T is modified via the norm of this curvature of a metric connection with totally skewed torsion HT. So these are the only two modifications at the level of the evolution equations. And then we have a constraint called the Bianchi identity, which now spoils HT from being away from being closed. So now it's not closed anymore. It has to satisfy this equation. And this combination means that we interpret this curvature as a two-form taking values in that joint. We take the wedge product of the two-form part, and we take the norm with respect to GT of the part valued in the adjoint. So now the system becomes more complicated, and now suddenly it involves connections with torsion, quadratic terms on the curvature of a connection with totally skew symmetric torsion. Either way, the evolution equation for the dilaton still decouples and therefore can be considered separately. Therefore, I'm proceeding exactly in the similar way as with the with the generalized Ricci flow. We define the heterotic Ricci flow after rescaling appropriately as the two-loop renormalization group flow of the common sector of heterotic string theory. It's the common sector because it's still GBH. We haven't modified the variables of the flow, but we are now considering it as a subset of a heterotic string theory and up to second order. And you may say, okay, but and then what happens with the third order and the fourth order? Are we going indefinitely? Order by order, this is nonsensical. Well, the expectation is that the Bianchi identity doesn't change, and higher order corrections can be absorbed into this quadratic term by modifying the connection. So instead of considering a metric connection with a skew torsion HT, one should consider a metric connection with more general torsion, which should be then subject to its own evolution equation. We are not going to do that here, but I just want to justify that this structure that we get at second order might be more definitive than it looks. So it's not a matter just of going order by order and keeping getting higher order terms here, but this is conceptually perhaps the final expectation that one should study. But this is up for debate in the physics literature, then well, it's not for us to decide at this point, I guess. So we say that a heterotic Ricci flow, which is a solution of this evolution flow, there is a family of dilatons, such as the dilaton evolution equation, it's satisfied. Okay, and well, here this is just a index notation for the formulas we have seen. So this combination that we were seen in the previous slide is just, as you are saying, as you can see here, a contraction of 3 indices of this curvature tensor. So you get a symmetric bilinear form. And just to show that the curvature of a connection with torsion is quite complicated, here you have the expression. So you got that square on this evolution flow. So, well, the first thing that we have to do here
Carlos,
is to
can you say something about the, so what is the signature of the pairing that appears in the Bianchi identity? Is it negative, definite, positive? I missed that.
It's positive, definite. Positive.
But this is like,
so everything is, yeah.
Okay, so can you go back one more, maybe? You had some other notation like GT or something.
Yes, sorry, I forgot to change that. Sorry, this is the good one, the newest one. So, because at the end of the day, since we are not using any abstract bundle, all the inner products are induced by the metric. So we don't need to use any other symbol. So we use the inner product induced by the metric on the endomorphisms, if you will.
But it's like taking traits.
Yes. Yes. Indeed.
Or
Positive,
minus.
definite. Exactly.
But you seem to get like the different sign from the usual convention for the Hall-Strominger system, no? Right? So this should be like this RGTHT should be the curvature of the nabla connection in the tangent bundle.
Yes. Well, that depends on your conventions when defining the system, because since we are not seeing at this point the supersymmetry equations, here you can change H to minus H.
I agree. Yeah, okay. Sorry. Yes, sorry.
So, no problem. So, well, the first thing we have to do is to realize that if we have an heterotic Ricci flow, then we can find a dilaton flow such as the complete system is satisfied for each cohomology class in H1. So fixing this, we get a linear parabolic equation, which by the standard theory of parabolic equations, always admits a unique solution such as phi 0 is 0. So therefore, we can forget about this evolution equation at this point for the dilaton, as I'm saying here, although it's important when one defines the solitons of the flow, because you also forget about this evolution equation. When you compute the solitons of the flow, then you have one less equation, but that depends on the perspective, I guess. Another point that I would like to make is that I'm presenting this evolution flow in terms of a family of 3 forms, which is not the most precise way of doing this, because this family of 3 forms is supposed to be part of the curvature on a category 5 principal bundle, or part of the data associated to a generalized metric on a transitive courant algebra. Since we don't have yet a proper formulation of this flow in this proper mathematical framework, either category 5 principal bundles or string courant algebroids, I won't use it in this talk. But that should be the right way to approach it. It's not going to be very important for us because we're going to focus very soon on the three-dimensional case. But this is worth pointing out that this flow naturally requires higher gauge theory in the sense of category 5 structures on principal bundles. So that's there, and this is this needs to be properly done for the heterotic Ricci flow. Okay, so
sorry, Carlos.
Yes.
When you set up the equation for the dilaton, this dilaton has to be imposed in order that all the system has solution. But the system depends on the systems depends on the string theory that you are taking. So how this will change it also? This will change also with the string theory that you're taking?
Maybe the dilaton flow equation won't change, but the evolution for GT will change for sure. Because something funny that happens here is that if you compute this in type 2A or type 2B, I think you don't get a quadratic term. You get a quartic term. So if I recall correctly, this is absent. So instead, the next term is fourth order. The first term after the first order is fourth order instead of second order. But that's so that seems to be truly a different flow. But then dualities in the string theory can do very crazy stuff. So I don't know if they can be still equivalent.
Yeah,
but they are seemingly different.
Yeah, and this new flow with this, let's say, the same dilaton flow, the same dilaton equation, will have solution.
I don't know if it's the same dilaton equation, but that I don't know. I haven't used these other flows because the goal for us was to do was to work in a framework which relates to the Hall-Strominger system. So that's why we focus on this heterotic computation.
I see.
But I don't say I don't know much about it. Mm-hmm.
Thank you.
Well, sure. If we're focusing on 2 dimensions, then H3 is 0, evidently, for dimensional reasons, and we recover the RG2 flow, which has been considered in the literature. And something perhaps interesting is that in higher dimensions, if we take HT equals to 0, then we obtain the RG2 flow, but then the Bianchi identity reduces to this condition here. And I'm curious to see if this condition is reasonable within the RG2 flow, if it singles out well-behaved RG2 flows, because this RG2 flow is already very complicated. So here it appears, but only with this extra constraint that needs to be satisfied with HT equals 0. So that's something. And in 3 dimensions, which is the dimension of interest in this talk, then the heterogeneous Ricci flow reduces to these 2 equations, which can be combined into this beautiful equation here in terms of a Ricci tensor of a connection with torsion HT, where we are writing HT as H0 plus dVt. We cannot do this in higher dimensions because HT is not closed in higher dimensions. One has to deal with the Bianchi identity. But in this dimension, this works. And then one obtains a simplified form. And also, since in 3 dimensions, the Riemann tensor, the curvature tensor can be written in terms of the Ricci tensor, we can expand this expression here purely in terms of the Ricci tensor of a metric. You see there is no Riemann curvature tensor here, and the dual of the 3-form H, which is now just a function ft. So this is a longer expression for the same flow, which may seem more complicated, but at the end of the day is more transparent for computations. So in 3 dimensions, this reduces to this complicated flow, and let's see what happens. Well, we have played a bit with this, but essentially the theory of this flow is open. As I write down these standard questions that one would like to solve for any flow, in particular this one. So, okay, so we have said a few words about the flow. Now let's focus on the self-similar solutions of this flow. So in order to properly compute the self-similar solutions of this flow, we need to, or a string structure. And since we don't have that formulation yet, we are going to focus on solutions of heterotic supergravity. And the point is that solutions of heterotic supergravity are automatically self-similar solutions of this flow. That's the claim, which I'm going to prove in 3 dimensions. So we can just focus on solutions of heterotic supergravity. And in this way, we are directly describing a subset of the self-similar solutions of this flow. So that's the relation. Heterotic supergravity solutions with trivial gauge bundle give a particular subclass of the self-similar solutions of the heterotic Ricci flow. Not all, but a large class, at least. So now we go to heterotic supergravity. We forget about the flow we just introduced. We keep in mind that heterotic supergravity connects with the self-similar solutions of this flow, but we don't need to further consider the flow until we, with the exception of proving later that these are actually self-similar solutions. So heterotic supergravity can be understood as the supersymmetrization of the Einstein-Yang-Mills system. So Einstein-Yang-Mills is a combination of Einstein-Hilbert and Yang-Mills, but it's not supersymmetric. So if you try to make this theory supersymmetric, then things doesn't work, and you need to add more variables to the theory, and you need to modify the theory. Since I'm running a bit low on time, let me be quick here. So heterotic supergravity requires some mathematical structure to be defined, and the basic perspective that one can get requires fixing a principal bundle, a positive definite inner product on the adjoint bundle, and a positive constant, which relates to the one that we have been discussing.
Sorry, Carlos, can I just interrupt?
And then, yes.
I was going to say, we don't really care
Yeah.
about strict time limit. In fact, we sometimes go much longer than an hour. So I just, in any case, yeah, take your time.
Okay, excellent, thanks. So there you go. So modulo formulations using categorified principal bundles and higher geometry. This is the basic stuff you get to define heterotic supergravity. And this was worked out in the physics literature back in the 80s in a tour de force of these two guys, Berchouf and Rho, who did all the extensive computations to show that these equations that I'm writing down here, and I will mention in more detail in a moment, are the bosonic sector of a proper, fully supersymmetric supergravity theory. And in doing so, they proved that in order to obtain supersymmetry, H needs to satisfy this Bianchi identity. And all this sounds familiar now from the flow we have been discussing. So clearly these two bad boys are related somehow, or should be. Here we have an extra actor, which is this curvature on this abstract principal bundle. But aside from that, we get some equations that resemble or look familiar with respect to the previous flow equations. So the combinations here are the same. So this is a contraction of three indices, etc., etc. Very well. So these equations define heterotic supergravity, but these are very complicated. If we only knew these equations, this would be good for nothing in a sense. This is too complicated. The interesting thing happens when one realizes that there exists a first order spinorial differential system that singles out a subclass of solutions of this complicated system, and which is simply determined by solving these first order relations plus some extra conditions. So given this supergravity theory, from the literature, we can extract this condition, which is that a solution of the previous system is supersymmetric if there exists a spinor in some given spinor bundle, which is determined by the theory, satisfying these extra conditions. Okay, so these are some extra conditions that you impose on solutions. The interesting point here to realize is that if you go all the way around, if you start with a solution to these equations that may not solve the solutions, the equations that I wrote down before, then you are almost there. And by a theorem of Ivanov, and I think someone else proved this in the physics literature before, maybe Waldron, I think, Gutowski. But in any case, by a theorem of Ivanov, if you have a tuple satisfying these spinorial equations, which are usually called Killing spinor equations, plus the Bianchi identity, then this is a solution if and only if this connection is an instant. Let me note that in relation to what I said before, more general formulation of these theories allow this nabla H to be any metric connection with torsion. So this gives, they obtain more freedom here. So now this is interesting because this now involves modern concepts in differential geometry. And these three equations are what is now today as the Hall-Strominger system. Essentially, these are the origin, the original Strominger system in a sense, in a spinorial form. It was Strominger who, working out this system, he rephrased it in terms of polystable holomorphic bundles on conformally balanced complex manifolds. So
Carlos,
solutions, yes.
If you go back to the previous slide, I think the theorem by Ivanov also tells you that if nabla H is an instanton with your conventions, then actually H is 0, A is flat.
That might be because this formulation in which
on a compact manifold.
Yeah, because this formulation for which we take here nabla H and not a more general connection with torsion is too restricted to study supersymmetric solutions.
Yeah.
But it's a very good framework to go beyond supersymmetric solutions, because supersymmetric solutions will be under control. But so it's in an interesting framework to see how one construct non-supersymmetric solutions. But yeah, that might be, it's very rigid. In any case, this condition is very rigid.
Okay.
So this is what I was saying. So what about non-supersymmetric solutions? So in order to study this system more closely and classify its solutions, we take P equals M. So we take this abstract gauge bundle to be trivial, and we reduce the system to these equations here. We have an Einstein-like equation for a connection with torsion. This is a Ricci tensor of a connection with torsion. We have a scalar equation, which we call the dilaton equation, and we still have the Bianchi identity. And these are the equations whose solutions are automatically subsimilar solutions of the heterotic Ricci flow. And that's the connection that I was saying. Heterotic supergravity with trivial gauge bundle, which means P equals M, gives us solutions to the subsimilar solutions to the heterotic Ricci flow. And of course, if we take the limit kappa going to 0, we recover a particular class of generalized Ricci solitons, right? For which this one form may not be exact. So it's in that sense, it involves a closed one form. Very well. So the most basic question one can wonder about this system, which also tries to extend well-known properties of the generalized Ricci soliton system to this corrected system, is that if we have a variational principle for this heterotic system, we call this system of equations simply the heterotic system. And the answer is that in general, you don't. And the reason can be traced back to this formula here, which is a very involved formula. It involves the equations of the system. But the reason behind this is the following. If you have a system of equations involving a Einstein equation plus equation for other variables, then a necessary condition for this system to be obtainable through a variational principle of some action functional is that the energy momentum of the Einstein equation has 0 divergence. And in this case, this doesn't have 0 divergence. And the failure of having 0 divergence is given by this equation that we wrote here, which you can see in the at the bottom of the slide, we call the strong condition, which is a Young-Mills-like condition for this nabla GH. So if we add this extra equation, which by the way would happen for free if we consider the heterotic supergravity in terms of a more general metric connection with torsion, which is then assumed to satisfy a Young-Mills-like equation. So if we impose this extra condition, then we satisfy this necessary requirement, and we obtain what we call the strong heterotic soliton system. So this is a nice way to justify this equation, which is sometimes which is sometimes imposed in the literature as saying that we impose this we impose this equation on the metric connection with torsion, mimicking the equation that the connection A here satisfies. So this connection, this equation for A is imposed on the nabla connection with torsion that people consider here more generally, and then they impose this equation just by analogy. Here there is a geometric reason to consider it and to obtain it. So this gives rise to the strong heterotic soliton system. And now that we have all the ingredients,
sorry,
this is, I think, a beautiful.
Can you say again?
Yes.
Can you say again? How do you relate the existence of a variational interpretation to the proposition? So, what is the proposition telling you? I'm a bit confused about that.
The proposition is computing the divergence of the Einstein equation.
Okay.
The Einstein equation is calligraphic E,
Okay.
right? And we compute it in terms of the Bianchi identity, which is calligraphic B, and the dilaton equation, which is calligraphic D. So ideally, we should get a 0 here, and we don't get a 0 here. And the failure to get a 0 is given by this expression in brackets here in the first equation, the first in the right-hand side, the first term.
Okay.
So if we impose this to be 0, then this is a necessary condition for this system to be Lagrangian, as people say usually. Because the generalized Ricci soliton, you know very well, it is Lagrangian, but it's not so clear what happened here. It's an interesting question. So we get naturally this extra condition, which can be obtained from the system, for example, as it is written in your papers, if you impose this metric connection with arbitrary torsion to be exactly nabla H.
Okay.
So it's another way of seeing why that's correct, instead of simply saying this is the same equation satisfied by this connection A. And
okay,
now this is.
I mean, if you take this string effective action and Borai with respect to the nabla connection thought of as a free parameter, you're also going to obtain this equation of motion for nabla, right?
Yes,
So
but yeah, but the point is that we want to have there are 2 points here. First, we want to have a variational problem for this system, which is more restricted. And second, the standard variational problem for the heterotic supergravity theory, as far as I know it, is always perturbative. So when people compute it, they always discard terms in kappa square or alpha prime square.
No,
I haven't done in the physics literature at least.
No, but you can do this exactly. That's not a problem.
You can do this exactly, but then you need to use this arbitrary metric connection with torsion, right?
Yeah, sure.
Okay. Yeah, in the physics literature, there is a variational problem for this system with this precise nabla GH, not the arbitrary one, but it's perturbative. So
okay.
it remains to be seen if there is some modification that can be done to make it exact.
Okay. Thanks.
And then a very beautiful result that connects the strong heterotic soliton system with the generalized Ricci-Soliton system is the following, which is a particular case of a statement proven in the paper by Baraglia and Hekmati. I should have written here the reference, which is that solutions to the strong heterotic system can be understood as generalized Ricci-Solitons on the total space of the frame bundle, but for a metric with a split signature. So this is quite interesting to me. The point is that you can lift the solution to the total space of the frame bundle, and then for a specific class of H, I won't get into this now unless you want to know. Many of you, I'm sure, know already. For a specific case, types of H, those defining real string classes, you get an equivalence. But interestingly enough, this shows that studying the strong heterotic soliton system is equivalent to considering generalized Ricci-Solitons of a split signature. That's I don't know. That's as I said, this lifting to this principal bundle is done generally in Baraglia Hekmati, but it hasn't been exploited in the literature, and I find this quite interesting. I wonder if the flows themselves can be related, namely if this heterotic Ricci flow can be lifted as to being a generalized Ricci flow, but for a metric of a split signature on the frame bundle of the manifold. Anyway, this is just another perspective on this heterotic soliton system. So, well, now we want to understand more in detail what happens with this heterotic soliton system and heterotic solitons, which I recall that they are the particular class of similar solutions of the heterotic Ricci flow that can be characterized as solutions of heterotic supergravity. And for this, we focus on 3 dimensions. And in 3 dimensions, we can rewrite, as I was saying before, the Riemann curvature tensor in terms of the Ricci tensor. We obtain this long equation in terms of the Ricci tensor and the dual of H. And the goal is to prove it. But before we prove it, solve it. And the goal is to solve it. But before we solve it, we show that if we have a solution of this heterotic soliton system in 3D, we have a natural heterotic Ricci flow, and simply flowing along the vector field bar phi. So that's the only issue. And well, the Einstein equation is easily seen to be satisfied, the Einstein evolution equation, and the evolution equation for the 3 form also follows by this computation. Some terms cancel out, and actually you get A0. So solving this system, we actually get self-similar solutions of the heterotic Ricci flow. This was given for free by heterotic supergravity, so we are happy to exploit it. We say that a 3-dimensional heterotic soliton is trivial if and only if this F is 0. This is the dual of H. And the first thing we recall is that if we have a non-trivial heterotic soliton, then this one form and the dual of H are related in this way. So the one form needs to actually be exact. We weren't assuming this. So it needs to be exact, and a potential for bar phi is actually the logarithm of F, so to say. So now this reduces the study of heterotic solitons in 3 dimensions to pairs. We go from triples to pairs, GF or G phi, depending on your taste. Well, this is just a general property that if we have a non-trivial heterotic soliton, they cannot be of a strictly positive scalar curvature. So that's a property. And the first thing that we do is to consider the case in which this F, which I will refer to simply as the dilaton, is constant. So if it is constant, then we have 3 families of solutions, which consist of manifolds, Riemannian 3 manifolds with constant principal Ricci curvatures. And we have the 3 possibilities there. The first possibility that just establishes the constant principal Ricci curvatures in terms of kappa. And there is no general classification result in this case. This is now a problem in Riemannian geometry of three manifolds by itself, which has been studied in literature, but it's not solved yet. In the second case, we have these conditions on the Ricci, on the principal Ricci curvatures, and then M is of this specific type. It's isometric either to SL2R or E1,1. And the third case, the M is simply a hyperbolic three-manifold. But we already see that despite the fact that supersymmetric solutions are rigid and flat, most probably, as Mario was saying, non-supersymmetric solutions, even with constant dilaton, are quite plentiful, at least from certain perspective. And this follows simply by noticing that if F is constant, then Ricci, the Ricci endomorphism satisfies some algebraic equation. So now we solve for Ricci and we get this principal Ricci curvature. So there are solutions. This is what we wanted to settle down. The first thing. And the problem now is, are there heterotic Ricci solitons with non-constant dilaton? This classifies the case with constant dilaton. What happens with non-constant dilaton? Well, we don't know. That's an open problem thus far for us. We don't know if there exists an heterotic Ricci soliton with non-constant dilaton in 3 dimensions. What we can say is that if we try on an arbitrary Einstein 3-dimensional manifold, then we have constant dilaton. There is no way of adapting that ansatz and getting a non-constant dilaton. And if we can somehow, the conditions of having constant principal Ricci curvatures that we obtain in this proposition, then we can rapidly encounter obstructions. This is one example. So if we assume that the dilaton is not constant and both the scalar curvature and the norm of the Ricci curvature are constant, which does not imply that the principal curvatures are constant, then M is diffeomorphic to the 3-sphere. And the reason is that we can construct, the dilaton itself would be a function with at most 2 critical values. And from that, it follows that the underlying compact closed through manifold needs to be a 3-sphere. So we have these results. There is a nice classification of heterotic solitons with constant dilaton. What we don't know if there exists non-constant dilaton heterotic solitons. So, well, these are 2 approaches one can adopt to construct solutions with non-constant dilaton, namely relaxing some of the hypotheses. Right now is a different approach, which it's based simply on deforming a given heterotic Ricci soliton with constant dilaton to see if there is a moduli space of such, or if it can be deformed on in order to obtain a heterotic Ricci soliton which has non-constant dilaton. And what I'm going to illustrate is that actually these heterotic Ricci solitons with constant dilatons are rigid within the class of all heterotic Ricci solitons. So they cannot be deformed into a heterotic Ricci soliton with non-constant dilaton. So in order to do this, we use the standard approach of moduli spaces a la Kuranishi, and following Koisho, we define, using a natural slice for the action of the diffeomorphism group on heterotic Ricci solitons, we define the notion of essential deformation, which is essentially a solution to the linearized equations of motion of the system, which is orthogonal to the tangent to the orbit of the diffeomorphism group. So this is a notion of infinitesimal deformation that cannot be eliminated through a Gates transformation. And in this case, a Gates transformation is a diffeomorphism acting both on G and F. Here, this mathfrak M represents the moduli space of heterotic Ricci solitons. We fix a given G, F, and the tangent space at that heterotic Ricci soliton is a subspace of the kernel of the linearization of the equations of motion, which is intersects the orthogonal to the tangent to the orbit of the diffeomorphism group at that point. And well, we define this vector space as the vector space of essential deformations of G, F. And what we want to show is that this G, F is actually zero. Here we are following Koishos rigidity results for Einstein metrics. Instead of applying it to the Einstein equations, we are applying it to the heterotic Ricci soliton system. That's the only difference. So we obtain first a couple of lemmas that relate, that restrict or constrain the admissible deformations, and then in particular prescribe the trace of a deformation H. H is a deformation of the metric G as being an eigenvalue problem for the Laplacian. Okay, so these are two formulas that we obtain manipulating the differential of the equations of the theory. And then we obtain that this vector space of essential deformations is actually flat. And the proof is simply based on the Weizenbuch formula for this differential operator that we call dg, which acts on one forms valued on the tangent bundle. So we consider symmetric two forms or symmetric bilinears as one forms taking values on the tangent bundle. Then we have the corresponding Weizenbuch formula, and we apply it to the equation that we had obtained in the previous lemma. And applying now this dg adjoint to both sides, then we obtain a monomial, a number of terms, which multiply the trace of H. And then verifying that this sum of monomials doesn't vanish, we obtain that the trace is actually constant, which then the previous eigenvalue problem implies that it's zero. And then from this, we arrive to the fact that the essential deformation actually vanishes. So the proof just relies in applying the Weizenbuch formula to a wise manipulation of the differential of the equations of motion, together with an infinitesimal slice condition obtained by taking the orthogonal complement to the tangent space of the orbit at the given point. And as a corollary to this result, we obtain that three-dimensional compact Einstein heterotic solitons with constant dilaton are actually rigid. And in a broader perspective, this is a rigidity result for compact solutions of a supergravity theory that we can consider as a rigidity result for compactification backgrounds of a supergravity theory. And we were not aware of any result of this type. Actually, in the supersymmetric setup, the opposite is true in general. Compact solutions to the Killing-Spinner equations, non-trivial ones, usually have large moduli. So that's something that we found a bit surprising. So, well, this is what we wanted to explain in this talk. And I think there are associated to this heterotic Ricci flow many potential future research lines. Some of them I have mentioned through the talk, but well, here there are several summarized. The first one for me is to develop the proper higher gauge theoretic formulation of this heterotic Ricci flow, compute properly all the heterotic the equations characterizing all the subsimilar solutions. And then there are questions related to basic analyticity of the flow in relation to computing what's the parabolicity regime, local existence. Well, this gradient formulation, I guess that's is too complicated. Then there are also open questions about moduli spaces of solitons in more generality, and the computation of more examples, left invariant solutions, adapted solutions on special types of manifolds like complex surfaces or Calabi-Yau manifolds. And what you can see, there are many possibilities, I believe. So that's all. Thanks.
Thanks, Carlos. Are there more questions? One comment I just thought I would make is in the three-dimensional case, even so you mentioned sort of like these solitons on compact complex surfaces, but I mean, really those solitons really sort of are products with a trivial S1, and they really sort of exist on S3. And I mean, I don't know. I have no idea if one should expect they correspond, of course, like kappa equals 0 in your case. I have no idea if you can like perturb those by perturbing kappa, but I mean, I don't know. It's maybe worth a try.
So you mean that generalized Ricci solitons on compact complex surfaces with the associated Hermitian metric and stuff, that those are only Hopf surfaces?
Yes. Mm-hmm. Yeah. And moreover, the metric is a product with a trivial metric on a circle.
On the universal cover. Yeah.
No, even just even before.
Okay.
I'm just saying. So in any case, forgetting that, my point is there is a family of non-trivial solitons on S3, which forms like a smooth family with a standard round trivial soliton.
I see. But perhaps I'm missing something very basic. But in your paper about these Gibbons-Hawking ansatz for generalized Ricci solitons, that's about 4 dimensions, right?
Yeah. It's not coming from that paper. Although in a sense, you can recover them in that ansatz, actually, I think. Yeah.
Oh, I see. Because in that case, in that paper, you also studying on compact ones, right? So
yeah. These come from an earlier paper. I can point.
Okay. Okay.
But yeah, my point is just for this like generalized 3D soliton equation, like kappa equals 0. There's nothing.
Yeah. Okay.
Well, there is a family on S3.
Yeah. So here, at least we have looked at 4D case as well, and there are more possibilities than those, because at least you can have suspensions of all the examples that I mentioned in 3D, which will be the analog of what you're saying, right? Essentially, you have x1 times s3. Here you can have s1 times all these 3-dimensional examples. Yeah. So you have more things, and if there are solitons with non-constant dilaton, which remains to be seen, then I would expect that there are other types of solitons in 4D for this system.
Sure.
Which then they might have a singular kappa going to 0 limit. But this already happened with these solitons, because if you recall here, kappa is dividing, so there is no limit here. There is no kappa going to 0 limit. That's interesting, actually. Yeah, these are genuine in a sense.
Can I also ask you, I forgot exactly where it was, but you defined something I think you called like a strong soliton or something like that. Can you show that?
Yeah, sure. It's the system, the theoretic system.
The previous one, or the
So this is the theoretic system.
Must have been the next one, I guess.
Yes, downstairs
no,
here.
next one. I don't know. I just saw it, but now I don't see it. It's where you define a
it's here.
strong soliton.
Yeah. Downstairs. There you go. A strong condition.
But you claim it only asks for like D star H equals 0, I think. I just saw it a second ago. I just don't know which slide it's exactly on.
Let me check.
Yeah, there it was. Yeah, it was. I guess it must have been 24. I think it's 24. This is 25. 24. Yeah, 24. Yeah, this sort of looks like the right solitonic system for me, but I don't know.
Yeah, it is. This is the generalized Ricci soliton.
Never mind. Never mind. I understand.
But this is this is in the total space of the. I still don't know how to wrap my head around this fact, which these solitons can be rephrased into generalized Ricci solitons in a split signature. That's something funny to me, but yeah. So actually, in a sense, we are trading instead of. So this is like if you studied generalized Ricci solitons with a split signature of a special type, of course, and you didn't like a split signature, and then you rephrase it in terms of a Riemannian metric, but then you get a more complicated system.
Yeah. Okay.
Anyway, yeah. It's something that I like to explore, but yeah.
Okay. Are there other questions?
Yeah. I wanted to ask two things.
Yeah.
So you mentioned that if you impose this strong condition, you have a variational interpretation, but it's not so obvious to me what it is. I mean, if I just write down the string effective action.
No, we don't have it. We don't have it.
Okay.
I just said that it's a necessary condition to have it.
Okay. What I mean is that even imposing that condition, if you just take the string effective action, this is going to give you some more complicated set of equations than the ones you have. If you take nabla to be nabla GH, this is going to give you further contributions to the Einstein equation, for example. So I don't know what is the right Lagrangian for this. Yeah.
Yes, I know what you mean now. Yes, I know. Yeah, indeed. But yeah. The thing is, I agree. The thing is that indeed that's what you that's the point of having a metric connection with arbitrary torsion, right? That is not coupled to H, and then when you compute the variation of H, it doesn't contribute.
Yeah, I guess this is one point. Yeah, my other question, I guess, is also related to this. So the motivation for is more like philosophical thing, but so your motivation for introducing this flow is the renormalization in the theoretic sigma model, right? But
well, it's more
my point is
it's more go ahead, sorry.
My point is the renormalization of sigma models is an ill-defined mathematical process, but as of today there are a few approaches, probably they are very sophisticated, to quantizing sigma models in mathematics. One is this BV quantization and this vertex algebra thing using the Carroll-Darran complex and so on. So if it would be nice to find a relationship between the flow that you are considering, its solitons, and one of these quantization of schemes which are now in the math community. What I mean is that my point is that I think we should not just take for granted that what is done in the physics literature, but we should also try to understand what quantization means and study the right conditions coming from that study, and not just take for granted that this loop expansion that physicists do is the right mathematical thing. I'm not sure. I haven't seen any thoughtful study of these loop expansions in math for nonlinear sigma models. This looks still very, like, I know, science fiction.
Yeah, I agree. I agree with you, actually. And actually, the point for me was not to study these renormalization flows, because that's not the way I arrived to this problem. Was just to justify these heterotic supergravity solutions as self-similar solutions of some flow. So we wanted to find of which evolution flow supergravity solutions are self-similar solutions of. And in doing that, in trying to find this justification, we arrived to this heterotic Ricci soliton, which then we thought was interesting by itself, because actually it's just a natural modification of the generalized Ricci flow with a quadratic term. But then our focus is on the heterotic system itself, so on the heterotic supergravity rather than the flow. I agree that this needs to be properly done mathematically. I fully agree with that. This is just you can, if you want, you can think of it as a proposal of a flow whose self-similar solutions contain all supergravity solutions of heterotic supergravity.
But I mean, I like the idea. I think there are even indications in the physics literature and in the math physics literature and even math papers that indicate that the thing you are doing is probably close to something related to the mathematical version of quantizing the sigma model. There are these constructions of the. It's something more refined than the sheaf of chiral differential operators. Is called the chiral structure sheaf of a manifold, and there is a twisted version using a bundle. And for those you get this anomaly cancellation equation with a tangent bundle rather than with two abstract bundles. So there is something special about the tangent bundle that should be related to the quantization of the sigma model in those terms. And it probably involves some special connection in the tangent bundle as you are using. I'm not sure if it is yours, but I think it's worth exploring further, like why they should be the right equations, and not just take for granted that what physicists tell us as is the right two-loop correction is the right thing. That's my only comment. Sorry about that.
No, it's very interesting what you just said. Actually, another point for us was to do this without introducing extra fields, so extra variables. So we wanted just to compute up or study a proper correction to the generalized Ricci soliton, which doesn't involve extra fields. And indeed, in what we have been doing, the fact that this is defined on the tangent bundle in the way it is plays a role. I think the result on the physics literature should be true, but I agree that this needs to be properly understood mathematically why and how unique the result is and how the scheme works properly. This result that you just mentioned, it's on a paper on Archive?
Yeah, this is... Yeah, I can send you the reference.
Okay, thanks. Yeah.
Okay, are there any other questions? Okay, let's thank Carlos again. That was a very nice talk.
Thanks a lot.